This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on a fascinating paper exploring conformal prediction for quantifying uncertainty in dynamic systems, specifically focusing on partial differential equations, PDEs. The authors propose using conformal prediction alongside established methods like Monte Carlo dropout and ensemble methods. What are the key challenges in uncertainty quantification for dynamic systems, and how does this paper address them?
The primary challenge lies in the cumulative nature of uncertainty in time series data. Traditional methods often focus on one-step predictions, neglecting the compounding effect of errors over time. This paper tackles this by introducing conformal prediction, a method with theoretical guarantees on coverage probability, even with finite samples. This provides a more robust assessment of uncertainty, particularly valuable in systems governed by PDDs, where small initial uncertainties can significantly amplify over time.
Conformal prediction is relatively novel in this context. Can you elaborate on its core mechanism and how it differs from the other uncertainty quantification methods used in the paper Monte Carlo dropout and ensemble methods?
Conformal prediction constructs prediction sets, not single-point predictions. These sets guarantee a minimum coverage probability for G95% based on a calibration dataset. This contrasts with Monte Carlo dropout, which approximates Bayesian uncertainty by repeatedly running the model with different dropout masks, and ensemble methods, which average predictions from multiple models. While dropout and ensembles provide uncertainty estimates, they lack the rigorous coverage guarantees of conformal prediction.
The paper highlights the importance of rotational invariance in visible systems. How does this factor into the evaluation of the uncertainty quantification methods?
Rotational invariance is a fundamental property of many physical laws. The paper tests the method's ability to maintain consistent predictions when the input data is rotated. This is crucial because a reliable uncertainty quantification method should reflect this invariance. The uncertainty should transform consistently with the data. The paper shows that conformal prediction handles rotational invariance more effectively than the other methods.
The paper uses a Navier-Stokes NS equation dataset for evaluation. Why was this dataset chosen, and what specific metrics were used to compare the performance of the different methods?
The NS equation dataset is a good benchmark because it represents a complex, real-world dynamic system with inherent uncertainties. The paper uses standard metrics like mean absolute error, MAE, root mean squared error, RMSE, and sharpness to assess predictive accuracy. Crucially, it also employs miscalibration area to evaluate the calibration of the uncertainty estimates, which is where conformal prediction shines.
The results show that conformal prediction, after recalibration, exhibits superior calibration compared to Monte Carlo dropout and ensemble methods. Can you explain the recalibration process and its impact on the results?
Recalibration, using isotonic regression in this case, adjusts the uncertainty estimates to better align with the observed frequencies of errors. While conformal prediction inherently provides valid coverage, recalibration further refines the uncertainty estimates, leading to more accurate and reliable prediction intervals. The paper demonstrates that recalibration significantly improves the performance of conformal prediction, bringing its miscalibration area close to zero.
The paper also investigates the performance of the methods on symmetry testing, specifically with 90-degree rotations. What insights did this analysis provide?
The symmetry testing revealed that conformal prediction, even after rotation, maintains relatively consistent MAE and RMSE values, indicating robustness. However, the sharpness metric showed some deviation, highlighting the impact of rotation on the predictive distribution's concentration. This analysis underscores the importance of considering inherent symmetries in the evaluation of uncertainty quantification methods.
The paper mentions using different neural operators, FNO, UNO, TF, and O. How does the choice of operator influence the results, and what were the relative strengths and weaknesses observed?
The choice of neural operator affected the overall accuracy and uncertainty estimates. TFNO generally outperformed FNO and UNO in terms of MAE, suggesting better predictive capabilities. ONO showed the poorest performance across metrics, indicating potential limitations in handling the complexity of the NS equations. However, after recalibration, the differences between operators were less pronounced in terms of miscalibration, highlighting the effectiveness of conformal prediction in improving calibration regardless of the underlying operator.
The paper concludes by suggesting future research directions. What are some of the most promising avenues for extending this work?
Future work could focus on developing more sophisticated nonconformity measures for conformal prediction, tailored to the specific characteristics of different PDEs. Investigating alternative recalibration techniques beyond isotonic regression could also lead to improvements. Furthermore, exploring the application of conformal prediction to other types of dynamic systems and higher dimensional PDEs would broaden the impact of this research. Finally, integrating uncertainty quantification directly into the training process of the neural operators could lead to more robust and reliable models.
The paper details the implementation of snapshot ensemble training. Can you explain this technique and its role in the overall methodology?
Snapshot ensemble training saves model parameters at various points during training, specifically at the end of each learning rate cycle, using cosine annealing in this case. These snapshots represent different local optima in the model's parameter space. By averaging the predictions from these snapshots, the ensemble method aims to improve robustness and reduce overfitting. This technique contributes to the uncertainty estimates provided by the ensemble method.
The paper mentions specific hyperparameters for the different models, FNO, UNO, TFNO. How crucial is the selection of these hyperparameters, and how might their optimization impact the results?
Hyperparameter selection is crucial for the performance of any machine learning model, and these neural operators are no exception. The choice of parameters like the number of modes, hidden channels, and rank significantly influences the model's capacity and ability to capture the underlying dynamics of the PDEs. Careful tuning and optimization of these hyperparameters, potentially through techniques like Bayesian optimization or grid search, could lead to improved accuracy and uncertainty estimates.
The paper uses a 70-20-10 split for training, validation, and testing. How sensitive are the results to this data split, and what are the implications for reproducibility?
The choice of data split can influence the results, particularly for smaller datasets. Different splits might lead to variations in the training dynamics and the generalization performance of the models. To ensure reproducibility, the paper should ideally provide details on the random seed used for the data split. Furthermore, reporting results across multiple random splits would provide a more robust assessment of the method's performance.
The paper provides visualizations of the results, including plots showing ground truth, model outputs, absolute differences, and standard deviations. How informative are these visualizations in understanding the performance of the different methods?
The visualizations are highly informative in providing a qualitative understanding of the method's performance. Comparing the ground truth with the model outputs allows for a visual assessment of the predictive accuracy. The plots of absolute differences and standard deviations provide insights into the magnitude and distribution of errors, which are crucial for evaluating the uncertainty estimates. These visualizations complement the quantitative metrics, providing a more comprehensive picture of the results.
In summary, this paper makes a valuable contribution by applying conformal prediction to the challenging problem of uncertainty quantification in dynamic systems. Its rigorous approach and theoretical guarantees offer a significant advancement over existing methods. Thank you for this detailed discussion.